Hi there, physics fans. In our last two episodes, I first talked about what we know about the Big Bang, followed by a description of the theory of inflation, which is an addition to the theory, and which solves some difficulties of the Big Bang of the 1930s. But neither idea talks about the actual moment of creation itself. That's an oversight I'd like to address in this week's episode of Subatomic Stories. What happened at the moment of the Big Bang or before, or even if the concept of before has any meaning at all, has long been controversial. In general relativity, the very idea of time itself is meaningless at the moment of creation. But we know that general relativity fails at very small sizes, so it doesn't really matter what Einstein says about the beginning of the universe. The truth is, we don't know about the moment of creation. But scientists have indulged in informed speculation, some of it even reputable. So let's talk about some of the ideas. Certainly, the safest and most reputable statement is that the visible universe was once much smaller. Perhaps the whole universe was infinite in size, or perhaps it was just much larger than the squashed version of our visible universe. The difference only matters to mathematicians and maybe philosophers. The fact is that, in the absence of data, we can't know. Physicists then make approximations, and, in this case, they approximate the fact we know to be true, which is the universe is way bigger than the visible universe, to something simple, which is the universe is infinite. Now, before the Big Bang, the part of the universe we can see was compressed to an incredibly small size. Different people have different ideas, but reasonable ranges put all of our currently visible universe from much, much smaller than a proton to something much larger, but still subatomic. But that was just a small piece of an infinite universe. The universe then began expanding. What caused that to happen? We don't know, but we know some established physics that would allow it. This is quantum mechanics, which allows for things to occur that are impossible if classical physics rules. For instance, there is the idea of quantum tunneling, which says that an object can appear on the opposite side of a barrier that common sense says is impenetrable. This is like a person finding themselves unaccountably on the other side of a wall that is 100 feet high. Of course, in quantum mechanics, it's electrons that can be in unexpected places, not people. But the point is that the laws of known physics allow for the seemingly impossible things to happen. Furthermore, in quantum mechanics, anything that can happen eventually will happen if you wait long enough. Maybe the compressed universe waited until a quantum fluctuation transitioned the universe into an expanding state. If that's true, then the next step was inflation, which took over, and then the traditional Big Bang. I talked about both of those in the last two episodes. Now, that idea sounds sketchy, but it's at least consistent with physics principles that we know to be true. But there are ideas that are even a little more speculative, so hold on to your socks. The idea of inflation, if it's true, can lead to another idea called eternal inflation. In that scenario, inflation is constantly occurring. A small location in an existing universe can, from those same quantum principles, start inflating. It's as if here in our familiar universe, a tiny region of our universe all of a sudden just started growing like crazy. And in internal inflation, the process can happen over and over again with an infinite number of universes butting off from other universes. It's kind of like a lava lamp where the blobs that form are like universes that go on to form other blobs or universes in our analogy. Speaking of lava lamps, there's another highly speculative idea out there. In this idea, our universe exists in a multidimensional space called a multiverse. In this idea, there are multiple disconnected universes floating around which can occasionally crash into one another. In this idea, the energy of the collision of our universe with another universe got deposited in our universe, heating it up and caused what we call the Big Bang. So, all of these ideas are pretty crazily speculative. You shouldn't believe in any of them. After all, we don't have any data for this early period in the universe. In fact, we're not yet sure even if inflation is a real thing. In the world's most energetic particle accelerator, we can only recreate temperatures that were common in the universe a tenth of a trillionth of a second after it began. That's 10 to the minus 13 seconds. That's pretty amazing if you ask me, but the simple fact is that it's late compared to what I'm talking about. Inflation is supposed to have been completely over by about 10 to the minus 32 seconds. I talked about that in the last episode, and before the Planck time, we know that all of our laws of known physics have to be chucked out the window when we need something to replace them. The Planck time is 5 times 10 to the minus 44 seconds, and I talked about it in episode 20 of Subatomic Stories. And, of course, all of the stuff I've talked about in this episode occurred before the Planck time. So the bottom line is that it's all very, very speculative. So you might ask, which one of these do I believe? I don't know. Anyone who claims that they know is a scoundrel, a liar, or a fool. There's just too much that we don't know for anyone to say anything with certainty. It may be a dissatisfying state of affairs, but don't know means don't know. But luckily, there are some things I do know, and that's a great segue back to the world of known science. Let's see what questions our viewers have for us this week. Question time, but first an admission. In episode 26, I said that if you had 5 stable quarks, that could make 125 different baryons, each containing 3 quarks. That was because each quark would be one of the 5 possible, and the result is 5 times 5 times 5 equals 125. But, as a viewer pointed out, that's wrong. A proton contains 2 up quarks and a down quark, but the order doesn't matter. A UUD, a UDU, and a DUU were all protons. So what I said was wrong. In the language of mathematics, the correct way to calculate is to use combinatorics, not permutations. And if you do it right, throwing away equivalent combination of quarks, you get 35, not 125. So it's embarrassing to have made a mistake, but that's science for you. People make mistakes, others correct them, and together we get to the right answer. And thanks again to Esquilax for catching the error. Reichaus notes that the most confusing part about the Big Bang is that it happens everywhere at once and that there is no center. Hi, Reichaus. Yeah, it was for me too, but it's actually not such a big deal, especially if the universe is infinite in extent. If it is, then you can pick a place and define your coordinate systems as starting there. Space goes off to infinity. Pick another spot and the same thing is true. In fact, it's true for all locations. No place is special. If space is curved like the surface of a sphere, the same thing is true. All locations are equivalent. So all are the center. And if space isn't curved, nor infinite, just large, then what I said isn't mathematically true, but it's practically true. And we won't know the difference until somebody invents some super-duper faster-than-light space drive. And if someone does that, we'll already have to rewrite the laws of physics. Arguing about infinities will be silly if that happens. Jaap Ongeveer asks if it's still true that everything in the universe came from something smaller than an atom. Hi, Jaap. Probably. But we have to be careful to distinguish between the visible universe, which is the part we can see, and the entire universe, which might well be infinite. Our visible universe was certainly much smaller and might well have been smaller than an atom. The exact size is not really known, but it was very small. Urvi Ari is confused by my explanation and notes that it looks like something is outside the universe. Hi, Urvi. This is a common question, and I think it arises from not being careful about the distinction between the visible universe and the entire universe. We actually can only see a small portion of the universe. We think that it is possible for an entity with godlike vision to see a much larger space than we can. Green Jeep Adventures asks if it's possible for chemistry to exist with atypical baryons and leptons. Hi, Green Jeep. In principle, the answer is yes. In practice, the answer is no. It comes down to lifetime. The longest-lived baryon that isn't a proton or neutron has a lifetime of about 1/10 of a billionth of a second. And the longest-lived lepton that isn't an electron lives for about 1/millionth of a second. So for chemistry to happen, a weird atom would have to assemble and then do a chemical thing. It's just very unlikely. Now, we have made muonic hydrogen, which is hydrogen in which the electrons are replaced with muons. Such atoms are much smaller than normal atoms, which can pack them together more closely. In 1956, physicist Luis Alvarez observed fusion in experiments with muonic atoms. So it's a real thing. Look up muon-catalyzed fusion if you're interested more. Fun fact, Alvarez, along with his son Walter, are the guys who figured out that a meteor killed the dinosaurs. Sandeep Maheshwari in English notes that there are many books and videos that say that there was no space before the Big Bang and wonders how that can be. Hi, Sandeep. It's easy to answer that. It's total nonsense. It's just not true. Now, I realize that me saying that will shock some people, and the physicists who say that aren't liars or fools, so obviously I have some explaining to do. Let's start with some truths. We know that Einstein's theory of general relativity is a good description of the universe. And if we take his theory as being perfect and run the clock backward, then the entire visible universe is compressed into a volume of zero size, literally, mathematically, zero. But, and here's a super key point, we know that general relativity doesn't work for something with zero size. The theory definitely breaks under those conditions. So what's really true? Well, we actually don't know. We don't have a theory of quantum gravity. So we don't know what happens to space compressed to such tiny sizes. Maybe space becomes quantized. Maybe the meaning of space, well, doesn't mean what we think it does. But we can be certain that a mathematical singularity of zero size with no space and no time is completely wrong. And there's a hugely important lesson in all of this, which is to understand the limitations of your theory. Any theory, and I mean any, will break if you push it hard and apply it in realms where it just doesn't cover. This is one of those cases, and if I may jump on a soapbox, it's common for physics popularizers, particularly theorists, to not distinguish well enough between what a theory says and reality itself. So when you hear a theoretical claim, caveat emptor. Carson Drawn asks if the universe was small at the moment of the Big Bang, how is it that cosmic microwave background is just getting here? Hi, Carson. It's actually pretty simple. It's basically like thunder. Lightning occurs essentially instantly, but you can hear thunder from a single lightning strike rumble for many seconds. That's because sound has a fixed speed and it takes time for sound to get to our ear. The same is true for light. This is compounded by the fact that the universe is expanding, so light has to overcome the expansion of space to get to us, like a boat traveling upriver has to overcome the motion of water. The bottom line is that the CMB was generated where we're standing now is long gone, but the CMB from more distant spots is only now just arriving, a full 14 billion years later. RedSims89 notes that there was some hoopla back when the Higgs boson was discovered, with some irresponsible journalists claiming that the universe might self-destruct. Hi, RedSims. So the story is kind of true, kind of. It's true that some researchers took electroweak theory and applied the measured masses of the top quark and the Higgs boson and concluded that the universe was in what is called a metastable state. A metastable state is a fancy word for something that will change if it gets a chance, but won't change easily. An example is a rock on the side of a mountain. It is true that the rock will eventually roll downhill, but it will also sit there for a long time first. In the case of the Higgs, the idea is that the laws of the universe aren't in the most stable configuration, and they might change in the future. If they do change, then things like atoms might no longer be stable, and that means that something like life would no longer exist. Scary stuff. Now for the truth. It's true that there was such a paper, and the measured Higgs boson and top quark masses pointed at the universe being in a metastable state. But let's be cautious. We know that the standard model isn't the final theory, it's an approximate one. Furthermore, the techniques for solving the equations is called perturbation theory, which is a form of approximation. In short, the false vacuum idea arises from an approximate solution to an approximate theory. That's still true, but it's likely that a better theory will change the outcome. So don't worry. I certainly don't. Lou Classens asks where one posts questions to get answered. Hi Lou, that's simple. You post them in the comment section for the videos. I read them and select a few. However, for each video there can be upwards of 1,000 comments, and I pick at most 10 questions, so the odds are low. And I usually select questions from a video no more than 2 days after it's posted. After that, it's rare that I see them. Questions are selected if they are succinct, and I think they would be of general interest to a broad range of viewers. Good luck. Stormtrooper asks if I watch YouTube videos and read papers that cover ideas that differ from the mainstream. Hi Storm. I don't have to. My mailbox is inundated with such things. I do look at them, but it's rare that such unsolicited manuscripts are of much value. Amateurs rarely have the training and background to make a substantial contribution. It's not impossible, just very rare. Now, that doesn't mean that the scientific community doesn't indulge in speculative ideas. Every month, physics journals are just full of crazy-sounding ideas from the theoretical community. And they do sound crazy, things like extra dimensions, multiverses, you name it. The difference between these papers and the amateur ones is that the professionally crazy ones are generally logically consistent and aren't falsified by existing measurements. Remember that my colleagues and I are in the business of breaking the laws of physics and pushing beyond known boundaries. It's what we live for. But that's very hard to do, and the self-criticism in the scientific community is simply brutal. So the short answer to your question is, I do look at a few, but I've never seen an idea that would survive professional scrutiny. And finally, Bonehead XXL1 asks how physicists know that the universe is 500 times bigger than the visible universe. Hi, Bonehead. What you said isn't quite true. We don't know how big the universe is. We merely know that it's no smaller than 500 times bigger. And we know this by looking at the temperature variations in the cosmic microwave background. Certain places are a tiny bit hotter or colder than average. Researchers look at the most common angle between adjacent hot or cold spots. If the universe is both flat and infinite, the most common spacing will be 1 degree. If the universe is curved like a sphere, the spacing will be bigger. If the universe is curved like a saddle, the spacing will appear smaller. So scientists measured the spacing and found that it was, a drum roll please, 1 degree. So that means that space is flat and infinite. However, that's not the whole story. I said they measured, and a measurement is only good if it's accompanied by an uncertainty on the measurement. Now, that 1 degree thing isn't so useful. You can convert it to what is called the curvature of the universe. The curvature is 1 over the radius of how the universe is curved. When you do that, you convert the 1 degree measurement to a curvature and get 0, which means an infinite radius to the universe, which means that it's flat and infinite in size. But that 0 came with an uncertainty. The actual number is 0.001 plus or minus 0.002. And that 0.002 is important. That means that the curvature of the universe could range from minus 0.001 to 0.003. But remember that the curvature is 1 over the radius, so we can just take the 0.002 uncertainty and flip it over. 1 over 0.002 is 500. That means that the universe is at least 500 times bigger than we can see. It may be more, but it can't be less. It's all pretty mind-blowing. Okay, on that grand note, I think I'll end the questions here. It's good to end on a big idea. If you enjoyed this episode, please like, subscribe, and share. And spend some time thinking about these big ideas, because the biggest ideas of all are physics, which makes sense because, even at home, physics is everything.